The second statement is actually will lead us to that conclusion. Which conclusion? The planet moves faster when it is closer to the sun than when it is farther away. It says a line from the sun to the planet sweeps out equal areas in equal intervals of time. What is the meaning of that? If this is the sun and this is the planet, the line joining the planet to the sun will sweep out. As the planet moves, that line sweeps out areas. Now, a very important law, a line from the sun to the planet sweeps out equal areas in equal intervals of time. Now, watch this. As the planet moves around the sun, these shaded areas indicate areas swept out by that line in equal time. Now, you see why the planet has to move faster when it is closer to the sun. In order to trace out the same equal area in the same time when the planet is closer, it has to cover a longer distance. You see that? Because the distance between the planet and the sun is small, it has to cover a longer distance along the ellipse so that you have an equal area like you cover when it is farther away. That means the planet has to move faster when it is closer to the sun than when it is farther away. That is the essence of the second statement. You must be familiar with it. A line from the sun to the planet sweeps out equal areas in equal intervals of time. Okay. Therefore, the planet moves faster when it is closer to the sun than when it is far away. All right. The third law, Kepler's third law is, it is a quantitative law. Look at the statement. The square of the orbital period. You know, orbital period is the time taken by the planet to go around once. The square of the orbital period of the planet is directly proportional to the cube of the average distance of the planet from the sun. Why the average distance? Because the distance of the planet from the sun vary with its position, because the orbit is elliptical. The square of the orbital period is proportional to the cube of the average distance of the planet from the sun. Well, if t is the period of the planet and r is its average distance from the sun, how will you represent this statement? We can say t squared equal to kr cube. Well, look at the little mistake there. The square of the period, the square of the period is proportional to the cube of the average distance. If r is the average distance, it means t squared equal to kr cube. So make that correction there, where k is a constant. Well, let me go back and get rid of it. Okay. Now, consider a planet of mass m sub p, mass of planet, in an orbit around the sun of mass m sub s, at an average distance r from the sun. All right? The centripetal force to keep the planet in orbit. You remember we talked about it. The centripetal force to keep the planet in orbit is provided by what force? Provided by the gravitational force between the planet and the sun. All right? If the mass of the planet is m sub p and the mass of the sun is big M sub s, what is the gravitational force between the planet and the sun if the average distance is r? If v is the orbital speed of the planet, then we have mv squared over r, which is the centripetal force. Centripetal force is provided by the gravitational force. This is the gravitational force. Big G ms mp over r squared. The universal gravitational constant times the mass of the sun times the mass of the planet divided by the square of the average distance between the planet and the sun. This is the gravitational force between the planet and the sun. It is this gravitational force that provides the centripetal force mv squared over r for the planet to go in the elliptical orbit. Alright, now you have mp, mass of the planet on either side will cancel. Is that right? This gives the orbital velocity v of the planet. Can you obtain an equation for the orbital velocity v of the planet? V equal to, I'm going to leave it for you to solve this. First of all, 1r on the left will cancel with 1r on the right. mp on the left will cancel with mp on the right. That gives me v squared equal to gms divided by r, or v equal to square root of gms divided by r. The orbital speed of the planet is square root of universal gravitational constant times the mass of the sun divided by the average distance of the planet from the sun. In fact, this equation can be used to find the orbital velocity of any planet if you know the mass of the sun and the average distance of that planet from the sun. Alright? And I have that over here, v equal to square root of g ms over r. Okay, if t is the period of the planet and r is its average distance from the sun, we have already used that. Tell me, how do you find the period? Period is the time taken for one complete revolution. In other words, period is the time taken to travel a distance of 2 pi r, which is, well, assuming that the orbit is almost circular. Now, v equal to 2 pi r, the distance traveled divided by the period. Is that right? If 2 pi, we assume that the orbit is almost circular. In that case, the length of the arc for one complete revolution is 2 pi r. And if the period, the time taken to do that is t, then the orbital speed v will be equal to 2 pi r divided by the period. Well, that will be, this 2 pi r divided by t is the orbital speed, and we showed earlier that the orbital speed v equal to square root of g ms divided by r. So, equating the two, we got 2 pi r over the period is square root of g ms over r. And you can actually get the statement of the third Kepler's law from this equation. Now, that means you square now both sides to get rid of the square root sign. 4 pi squared r squared over t squared equal to g ms over r. And can you solve this equation for t squared? Now, what is the statement of the third law? The third law says t squared is directly proportional to the cube of r. T squared is proportional to r cube, or t squared equal to k r cube. Is that right? Alright, can you solve for t squared from here? T squared will be equal to, you can see when you cross multiply, t squared equal to 4 pi squared times r cube divided by gms. And look at the way I wrote it. T squared is 4 pi squared over gms multiplied by r cube. Why did I write it like this? Because 4 pi squared over gms is a constant. G is the universal gravitational constant. ms is the mass of the sun. So 4 pi squared over gms is a constant. That's how k. Didn't we start by saying that t squared equal to kr cube is the third law of Kepler. So you can see this statement that we got from using directly Newton's law of gravitation. Now, you see the merit of Kepler's law is that Kepler formulated this law. This is Kepler's law. T squared equal to kr cube. Kepler formulated this law long before Newton came up with his gravitational theory. And look how both these agrees. We got this equation using Newton's gravitational law, and it led us to Kepler's law. That means Kepler's law, which was formulated long before Newton's law of gravitation, both are equally true. Now, what is therefore this k equal to, the constant in Kepler's law? For the solar system, for the planets that move around the sun, this k is 4 pi squared divided by gms. So k equal to 4 pi squared over gms. So if I ask you, what is the value of k for Earth? In other words, when the Earth moves around the sun, the value of k is this. What is the value of this k for Venus? The same thing. What is the value of k for Jupiter? The same thing. For all planets in the solar system, the value of k is the same. On the other hand, if you now want to talk about the motion of a satellite around, say, planet Jupiter, then Kepler's law can be applied there. But it is the satellite that is moving around, and in place of the sun you have Jupiter. So k in such a case will be obtained by replacing the mass of the sun here by mass of Jupiter. Okay? All right. Compute the value of